Welcome back to ajspeller.com. In today's tutorial, we're going to use the TI-84 plus C to model the following problem that we've solved in a previous tutorial. A ladder is 25 feet long. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is sliding away from the wall at a constant rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet, 15 feet, and 24 feet from the wall? We've solved this problem already analytically, and what I've done is I've created a concise table here at the bottom to actually show what those results were. So when we were 7 feet from the wall, we found that dy dt was this value. At 15 feet, we found that. At 24 feet, we found that. What we're going to do now is use this information and actually model it using the TI-84. And this here is the implicit function that we use to relate to this problem. And then when we made it into a parametric equation, these are the values that we used for x and the values that we used for y. All right, so let's go ahead and take a look at the calculator. First thing you want to do is check the mode. You need to make sure that you're in parametric mode and also need to make sure that you're in simultaneous mode as well. Next thing you want to do is to go ahead and enter in these values for the parametric equations. And for speed, I've already put those values in. Here, the green, it represents the position of the foot of the ladder at a particular point in time. The orange represents the top of the ladder at a particular point in time, and then the red is where I put the foot of the ladder, or the green and the orange together, so we can see that modeled with a red color curve. All right, next thing we want to do is we want to check the window. Here at the window we have a minimum value for time starting at 0. But for this problem, since the length of the ladder changed and the rate at which the bottom of the ladder is moving has also changed, we need to figure out what the new time maximum, or T max value, will be for this model. So to do that, we're going to use the distance formula, or one of the distance formulas. The formula we're going to use here is distance is equal to the rate times the time. The distance here is going to be the length of the ladder, which is 25. The rate is going to be dx dt, which is 2, and we're trying to figure out the time. Well, to isolate time, we need to divide both sides by 2. So we're left with t is equal to 25 halves, which means take half of 25, and we see that the time turns out to be 12.5. So here in the calculator, we're going to arrow down, and for t max, we're going to put in 12.5, or 12.5 seconds. The step is still going to be at a rate of a tenth. The x minimum is going to stay at -1. The x max, we're going to change that from 13 to 26. And the reason why we're using 26 is because the length of the ladder is 25 units. We want to go one more unit, or a foot longer, so that it appears so it looks good on our model. We're going to keep the x scale the same. Y minimum is also going to be at -1, and y minimum is going to stay at -1, and y maximum is going to also turn or be changed to 26, again because everything is taking place in the first quadrant there. So once we have all that in place, next thing we want to do is we want to graph to take a look at what we have here. All right, what I want you to notice is that the bottom of the ladder is moving at a constant rate, and the top of the ladder is accelerating, so it's getting faster and faster as it approaches the ground. And let's take another look at that so that you can see, so you can focus on that. So we went second and then click the program button. We want to clear draw, and that's going to draw it again, and we see this is the manner in which the simulation is run. Next thing we want to do is we want to go ahead and we want to verify each one of these results. So to do that, first thing we want to do is we need to figure out the times at which the bottom of the ladder is 7 feet from the wall, 15 feet from the wall, and 24 feet from the wall. And to do that, we're going to use one of the distance formulas again. We're going to stick with distance is equal to the rate times the time. When we're dealing with the x equals 7, the distance is going to be 7. The rate is still going to be 2. And we're going to put in t for time because that's what we're trying to figure out. We take half of both sides. Now we've isolated it, so now we have t is equal to 7 over 2, or half of 7, and half of 7 is 3.5. So we're going to use this value later when we go to calculate dy dt. Let's go ahead and figure out at what time the bottom of the ladder is going to be 15 feet from the wall. So again, we're using distance is equal to rate times time. This time the distance is 15. The rate stays at 2, which is dx dt, and we place in the variable t. Again, we're going to take half of both sides. These t's cancel, those 2's cancel, leaving a t. And then we have 15 halves. Well, half of 15 is 7 and 5/10. So we're going to use that for the second one. And then when we get to the third one here in green, again, we're using the distance is equal to the rate times the time. This time the distance is 24. The rate is still 2. And we have t for time. Divide both sides by 2 to isolate the t. Those 2's cancel. So here we have 24 halves, or half of 24, which is 12. So we're going to use these values each time we figure out what dy dt is, or the rate at which the top of the ladder is moving when we're at these particular snapshots in time. All right, so let's go back to the tool. This time we're going to use 3.5 to figure out if it's going to come, if dy dt remains at the negative 7/12 feet per second. So we're going to press on or click on second, and then press the trace button. We want to figure out what dy dt is, so we're going to arrow down to 3, press enter. And what I want to do is I want to again press down until I'm on the red, which is this curve here. And the time that I want to put in is 3.5. So I type that in and then press enter. And here I see that dy dt is negative 0.58333 repeating. So now let's do second quit and put that in to verify its fractional equivalent. And that's negative 0.58333. So second quit. So we have negative decimal point 58 and several 3's. Press the math button. It's already set to fraction, so we're going to convert that to its fractional equivalent. We press enter 2 times, and it did not change. Let's see if we can do that again to try to figure out what our mistake was here. So negative 5, whoops, not 5. So negative 0.58, several 3's. Let's put a few more 3's up here, and then do math, and then 1, and then 1 again. And we see this time we did come out to negative 7/12. I didn't add enough 3's, so let's go back and just verify. And we see this here did come out to be negative 7/12. Now let's input a time of 7.5. So let's go back. Let's go to graph. Let's type second and then trace. We want number 3 for dy dt. We want to make sure we're on the red. So we arrow down, and this time we want to use 7.5 and press enter. And here we see we came out with dy dt equals negative 1.5. So let's do second quit. Let's put in the negative 1.5 and then press math. It's already on fraction, so just press enter. And we convert negative 1.5 or negative 1 and 5/10. We get a negative 3 halves. And we see here we also have a negative 3 halves. And now to the last one, our time should be, or t should be 12. So let's go back, press graph. Let's go to second and then trace. We want number 3, which is dy dt. Let's make sure we're on the red curve. And then let's type in 12 and then press enter. Here we see that dy dt is equal to negative 6.857146. And now let's go to second and quit. And let me just write that in. So it was a negative 6.857146. We can't do the math and then fraction because the calculator actually truncated some of the decimal places afterwards. So we'll just put this here so we can visually see it. And what I want to do is go back now and just do the division, which is negative 48 divided by 7. So here we're going to show negative 48 divided by 7, and we should see the decimal equivalent. And we see that the decimal equivalent, it's approximately the same. Again, there were some digits lost during the calculation, but this here is close enough where 1, 2, 3, 4, 5 digits after the decimal point in accuracy. All right, so what I want to do now, just as a last step, let's just go back to second and then program draw, and I want to do clear drawing because I want you to see that model one last time. So here we press graph, and we see here that everything is drawn in. All right, guys. Well, that there sums up another tutorial by ajspeller.com, and as always, thank you for watching.